So next talk is an invited talk given by Darius Modirrousta-Galian on role of planetary winds in planet evolution and population. So the alarm at 25 minutes.
Okay, I'm just trying to figure out what the buttons do. Okay, so thank you for having me here. It's a great pleasure to be at this conference. My name is Darius Modirrousta-Galian, and I work at Yale University. And today I'm going to give a review on how atmospheric evaporation shapes exoplanet populations. And I think a good place to start is by looking at the data we have had through time. In 1988 was the first time that an exoplanet was suggested in the literature. In 1995 was the first time an exoplanet was officially confirmed in the literature, and the two authors got a Nobel Prize. In 2009 was when we had the Kepler mission become active, and in 2014 was when we had an explosion in exoplanet discoveries because of the immense success of the K2 mission. And this year, for the first time, we know over 5,000 exoplanets. So now is really the time to begin doing the research, the immense amount of research with JWST, Ariel, Twinkle, and many other missions that are soon coming. So the natural question to ask is, well, what are the population trends? What do we know about the trends of exoplanets? And before we look at the data, I think it's a good idea if we see what theory predicted before it had access to this data. And I reckon a good place to begin is with the models of Ida and Lin. And what they did was they created a formation simulation that took, it considered all of the factors required to build a planet. This includes grain condensation, runaway planetesimal coagulation, oligarchic growth, gas accretion, and many other factors. And they even included different types of stars. And what they found is that the distribution of the rocky embryos of planets follows an exponential decay, meaning that smaller mass rocky planets are significantly more probable than heavier mass rocky planets. Now, when you take into consideration gas accretion, then the distribution changes a bit, and you can see that by the peak in the bottom graph, but we're not interested in that. What we're more interested in is in the distribution of the rocky embryos. And this work was further investigated by Ikoma and Hori. And what they did was they took these rocky embryos and they migrated them through the protoplanetary disk to see how much gas would they accrete in the early stages of their life. And what they found is that, very roughly speaking, approximately, planets accrete about 1% of hydrogen gas, 1% relative to their mass. And yes, they considered various factors, like the temperature of the protoplanetary disk, the density, the opacity, whether you have grains or not, the lifetime, how long the disk lasts, and so on. But roughly speaking, 1% is what they found. And this is interesting, because now we're beginning to have a story. We can say, we know the distribution of the rocky embryos, we know approximately how much gas they accrete. Can we make some predictions for what the radius distribution of these planets will be? And this is what Mordesini et al. 2012 did. They created a formation simulation that included all of these factors I've just explained. And what they predicted is that the distribution of exoplanet radii should follow approximately a skewed Gaussian. And you can see the red line over here is the prediction they made, with a peak at about 2 or 3 Earth radii. And the observations available at the time is shown by the blue line. And you see everything just worked. The formation of the rocky embryos, the gas accretion, the geophysical analyses they made, such as the luminosity of the central embryo. And then it all connected with the available data like clockwork. It all just worked. In fact, we were very happy with the results. The authors said, we are now able to characterize extrasolar planets in their most important physical quantities, like semi-major axis, mass, composition, and luminosity, from one single model. And this was the way things were. We were very happy with this result. But then something shocking happened, something that we did not expect, something that blew our minds. As more and more data was collected, we found that rather than there being a Gaussian distribution, there was a bimodal distribution of exoplanet radii, with one peak at 1.3 Earth radii, the other one at 2.4, and the minimum point at 1.75 Earth radii. And in fact, the distribution is so statistically robust that the authors of this paper, Fulton et al., 2017, actually gave the planets different names. The first peak they called super-Earths, and the second peak they called sub-Neptunes. But there's a reason, a specific reason why they use these names, and you can see that from the second clue they gave us, the second piece of data, and this is it. If we plot the orbital period of a planet, the orbital period of planets, and the planet size, and then we put in this graph different data points, you get this. And if I were to ask the data-driven scientists in this room, or the observational astronomers in this room, what planets would be the easiest to observe? The answer would be planets that have large radii, because they block more of the stellar light, so you get a greater drop in the apparent luminosity of the star, and planets that are closely orbiting to the stars, because then you get more measurements because they orbit more quickly around the star. So these planets should be the easiest to observe. But here's the shock. We have a lack of planets in this quadrant. There is a drop in the occurrence rate of planets in this part of the graph. And this was shocking. And what the author suggested is that actually what happened is that planets used to be there, but then they lost their atmospheres. And because they lost their atmospheres, they migrated downwards to the quadrant below. And this was interesting to theoreticians. They saw this and they said, well, what causes the bimodal distribution? And what causes the subjovian desert? And different mechanisms have been proposed. One of them is that it's interior energy from the planet that is driving atmospheric evaporation. So if you have a very, very, very hot planet in the inside, and this planet has an atmosphere, it will lose that atmosphere, presumably. The second argument is that it's not interior energy that's driving mass loss, but it's X-ray and ultraviolet irradiation from the host star. And it's slowly eroding away the atmosphere of planets. And that's why you get one peak, presumably without atmospheres, and the second peak of the distribution, presumably with atmospheres. And the last mechanism is independent of atmospheres, at least not in a direct way. What it poses is that this bimodal distribution is a natural quirk, a natural outcome of planet formation. What they argue is that the first peak of the distribution is composed of planets that are rocky, like Earth. But the second peak, rather than being rocky planets with primordial atmospheres, you have planets that are rich in ice. Picture, for example, Jupiter's moon, Europa, or Saturn's moon, Enceladus, and make that bigger. Make them 10 or 15 Earth masses, and that is what they suggest is occupying the second peak. Now, unfortunately, because of time constraints, I can't talk about all of these mechanisms, so in this talk, I'm going to talk about these two. And then if you have any questions about the third one, I can try my best to answer them after. So the first mechanism was actually birthed in Earth and planetary sciences, because it has been suggested for quite a while that planets that are the size of Earth or larger go through a period called the giant impact phase, during which planetesimals collide with each other and merge. And this is how they grow in size. And during this merging, there is an extreme loss of energy, an extreme transfer of energy, and surface temperatures can be incredibly high. Simulations of Earth show that during the giant impact that formed the moon, temperatures could have reached 10,000 Kelvin or higher. In fact, Shun Karato suggests that depending on the equations of state you use for the magma ocean, temperatures could have been 15,000 Kelvin. That's hotter than the surface of our sun. So if you have exoplanets with primordial atmospheres that are 10 or 15,000 Kelvin, you will probably lose your primordial atmosphere. So this is the crux of this argument, that if you have a primordial atmosphere, a planet with a primordial atmosphere, and it's hit by one of these giant impacts, temperatures of 10 or 15,000 Kelvin will cause the atmosphere to go, to disappear. When making this model, the authors made several assumptions. One of them is that these very, very hot planets cool uniformly and isothermally. And this is not quite right, because when a magma ocean is that hot, it convects very, very vigorously. So rather than being isothermal, it will be adiabatic. Furthermore, the way a magma ocean cools is not the same way that, for example, water crystallizes. Because magma is made of different minerals, it crystallizes over a range of temperatures. And the details of this range are given different names. For example, you can call it the solidus, the liquidus, the rheological transition. These are terms used by earth scientists and planetary scientists, and they matter. When you're dealing with a magma ocean, they matter. These details matter, but they were not included in this model. Now, I don't have enough time to go into what these terms mean, but fundamentally, it means that a magma ocean cools it crystallizes in different stages, and these have to be included in any magma ocean model. However, the major flaw of this mechanism is that it cannot explain the subjovian desert, this being that planets that are closely orbiting to their stars are not likely to have large atmospheres. Of course, this model cannot explain that, because it is by definition independent of the star. It is by definition only dependent on the interior energy of the planet, so it cannot explain the subjovian desert. It can, however, explain the bimodal distribution. And here you can see their simulation compared with the available data, and they were able to produce this bimodal behavior. The second model for atmospheric evaporation is X-ray and ultraviolet induced photoevaporation. Stars are very luminous in these bands when they're very young, and they could erode away the atmospheres of planets. And there's been a lot of research on this for decades, but in terms of sculpting and changing exoplanet populations, this was really popularized by the work of Owen and Wu in 2013 and 2017. And what they suggest is that the bimodal distribution is consistent with planets that are approximately 3 times the mass of Earth, half of them having primordial atmospheres, and the other half not having. And not only that, but they're able to reproduce the subjovian desert. Of course they can, because planets that are closer to the host star are more highly irradiated in X-ray and ultraviolet irradiation. So they're more likely to have their atmospheres removed by this high energy irradiation. So it can explain this as well. So far, so good. And this is the model they used for simulating mass loss. It's called the energy limited approximation, proposed by Watson et al. In 1981. And the main parameters are the photospheric radius, RP, the XUV absorption region, RXUV, the XUV flux, FXUV, and the mass of the planet, M. And the other values you see are just constant. Now, there's something interesting about this equation. There's something a bit strange. If I take a rock and I heat it up by 100 Kelvin, how much will the volume change? Well, not by much, because the thermal expansion coefficient of rock and many solids is very low, very small. But if I increase the temperature of a gas by a few hundred Kelvin, the difference in the volume will be significantly more, because gases are incredibly sensitive to temperature. We know this from the ideal gas equation. So where is the temperature dependency on this equation? There has to be one. We're modeling the loss of gases. There has to be a temperature dependency. Where is it? It isn't included. And if you really want to see what the problem is, we can look at these 2 planets. The first one has an effective temperature of 31 Kelvin, and the other one is orbiting a star, a B-type star, that has a temperature of 30,000 Kelvin, and that's why the planet is about 7,700 Kelvin in temperature. Now, for the sake of argument, let's imagine that both these planets had the same mass, the same radius, and they were exposed to the same XUV flux, just for the sake of argument. Imagine that. The energy limited approximation would predict the same mass loss even though they have a difference in temperature of almost 7,700 Kelvin. And this is the problem with this model. It does not take into consideration temperature. And this has been investigated by various authors that said, well, what happens if you do take temperature into consideration? How will the mass loss be when you take temperature into consideration? And one such author was a speaker yesterday, Darius Modirrousta-Galian, who published this wonderful paper a few years back. And what they do in this paper is they run fluid dynamical simulations that include chemistry and temperature and XUV flux to see what the mass loss rate will be. And here's how you read this graph. The y-axis is a ratio between the energy-limited approximation and the fluid dynamical estimations they make. Sorry, I should say simulations. And the x-axis is the Jeans parameter, which is defined as the energy of a particle, the gravitational energy of a particle, divided by the thermal energy of a particle. And as you can see on the graph, when you have a large Jeans parameter, i.e. low temperatures, the difference between the energy-limited approximation and the fluid dynamical simulations is roughly small, approximate, roughly speaking small. But as soon as you start having a small Jeans parameter, i.e. very large surface temperatures, the difference becomes huge. 1 order of magnitude, 2, 3, and then as you have higher and higher temperatures, i.e. smaller Jeans parameters, it becomes 7, 8, and 9 orders of magnitude difference. 9 orders of magnitude. Why? Because temperature matters. You have got to include temperature into your model. And this got me interested. I said, well, if mass loss is that affected by temperature, can you still reproduce the bimodal distribution of exoplanet radii and the subjovian desert when you take temperature into consideration? So I ran a population simulation, and indeed I found that yes, you can still get this bimodal behavior. The red line is the distribution of planets before they experience atmospheric evaporation, and the blue line is after. We also found that there is a transition region where about 50% of all planets have primordial atmospheres. And then we found as well that there's a small peak here composed of planets that are larger than 10 Earth masses, but they don't have primordial atmospheres. And there is a name for these planets. It's mega-Earths, and they have been observed in the literature. We have found some planets that are larger than 10 Earth masses, and they don't have primordial atmospheres. And we were also able to reproduce the subjovian desert. As you can see, this is the subjovian desert, and this is the bimodal distribution. Great. Problem solved. Right? No, something's wrong. Do you see it? Do you see what is wrong? What's this? These planets have very large radii, but that's weird, because in our simulations, we considered very large hydrogen atmospheres. In fact, we considered some planets that have very small embryos and very large atmospheres, and yet we find some planets that have very, very large atmospheres. How is that possible? Well, when you investigate it further, you find something shocking. There are some planets observed that have densities lower than pure, cold hydrogen gas. I'm not making a mistake here. Planets with densities lower than pure, cold hydrogen gas. How is that possible? How can you get that? Well, there's only one way you can get that. Only one. And it's if these planets are incredibly, insanely hot inside. Because gases are so sensitive to temperature that if a planet is very, very hot, it can have a radius larger than cold hydrogen gas. And look at the age of these planets. 500 million years. In fact, DS took AB is 40 million years old. These are baby planets. They are very, very young, and they have a lot of energy from when they formed. A lot of their accretion energy is still inside. But now we have a problem, because for these planets to be this, have such high densities, such large radii and such low densities, you need high interior energies. But if you have high interior energies, you have core-powered mass loss, which we discussed earlier. So now we have the problem. What is it? Is it photoevaporation, or is it core-powered mass loss? Photoevaporation can explain the subjovian desert and this bimodal distribution, but it can't explain the big radii. But core-powered mass loss can explain the big radii and the bimodal distribution, but not the subjovian desert. So which is it? And I think you know where I'm going with this. For you to explain all of these observations, you need to have both mechanisms together. And this is what I've been investigating with my supervisor, Professor Jun Kurinaga. Here's a plot of our model using different approaches in the literature. And you have the mass loss rate and you have the surface temperature of the planet. Our model is given by, we have two models. One is the blue line and the other one is the orange line. The blue line includes diffusion limited mass loss and the other one does not. Now, if we focus on the orange line, you can see that when surface temperatures are low, our model approaches the model of Daria-Kubishkina for hydro-based, X-ray and ultraviolet-induced atmospheric evaporation. But as soon as you start increasing the surface temperatures, the two models start to deviate. Of course they do. Because now you no longer have X-ray and ultraviolet-induced photoevaporation. Now mass loss is dominated by the interior energy as opposed to the external energy from the star. That's why you see these two models deviate, as you have higher and higher interior temperatures. And in fact, we found that when you include these two models together, you start getting some emergent properties that you would not have predicted if you just had them separate. We find that mass loss can be divided into three different categories, regime 1, 2, and 3. Regime 1 is when mass loss is completely defined by the interior properties of the planet. Regime 2 is when you have a transitory state. And regime 3 is when mass loss is dominated by X-ray and ultraviolet irradiation. So, the results. What I'm suggesting is first, that the question we should be asking is not whether X-ray and ultraviolet-induced photoevaporation or core-powered mass loss are responsible, but rather they both matter. They are both important parts of a planet's story as it loses mass. You have got to include both in your model. And 2, a planet evolves drastically as it ages. Look at planet Earth. When Earth formed, surface temperatures could have been 10 or 15,000 Kelvin, according to some simulations. But if you look at Earth now, it's much cooler, much friendlier to life. You have got to include this evolution into consideration when you're modeling mass loss. So the question, the future work that I'm interested in is, if you include both of these mechanisms together, can you still produce the subjovian desert and the bimodal distribution? Or do you need something else? This is the way, this is the direction that I think would be interesting to investigate, and current efforts are in place. So with that, I thank you all for listening. It's been a pleasure, and if you have any questions, I'll try my best to answer.
So thank you for keeping your time. We have 7 minutes for questions and comments or... Okay, please go ahead.
Hey Darius, great talk. My eyes twinkled when you mentioned DS2KB. I've been fascinated about that planet since its discovery.
Yep.
I've been leading 2 programs on HST to observe atmospheric escape in that planet, and we actually just got a visit last week, which is exciting. Do you think that, I understand that your study is based on the population of exoplanets, but do you think that if we can constrain the atmospheric escape rate of individual planets to a degree of factor of a few, more or less, do you think we can discern if one of these mechanisms dominates over the other, or if it's a combination of both or all of it? Just by observing individual planets and not the population itself.
Right. So just to clarify, one of the papers I've been working on is specifically on the details of atmospheric evaporation and not just population analysis. But my answer would be yes. That if you can constrain it through observation. In fact, I think only through observations you can really begin understanding the precise details, because in the early stages of a planet's life, when it's interior energy that's winning, that would be what's running mass loss. So what you can do is you can say, well, let's ignore interior energy and see how much mass loss you would predict with just XUV. And then you can compare that with observations. And if you see that they don't match, then that would suggest that the XUV model does not apply in planets when the interior energy is very high. And we know the interior energy is very high because of its immense radius. It's got a huge radius.
Yeah, yeah. But we don't know its mass yet.
We don't know its mass, but there's a new paper that suggests it's probably less than about 10 Earth masses.
Yeah, yeah, yeah.
So once you, considering that it's less than 10 Earth masses and it has a radius similar to that of Saturn or Jupiter, we know it's very energetic inside. So it is through observations and constraining the mass loss rate that we can really start seeing what mass loss model applies and when, and if it matches with theory.
Perfect. Thank you.
Thank you for your question.
Okay, other questions, comments?
Hi, Darius. Great talk.
Oh.
So when we do population, we typically look at radius versus period or orbital separation because we are essentially Kepler biased. But can it be that we are being fooled by nature and things are a lot more complicated? We have also planetary mass, we have stellar mass, we have age, we have many things that all play together somehow. Can it be that we are just looking things on a, just in one plane, and we're not understanding the picture because we missed all the other planes?
Yes. Could you be a bit more specific if you're referring to a particular point or?
No, it's a general consideration.
Right. I agree with you that there's many factors to a planet that, and the more we know of these factors, the better our models can be. What I'm doing here is I'm focusing on the most important factors in the early stages of a planet's life. Of course, for example, tidal heating could play a role. Radioactive decay is important in heating the interior of the planet, but they don't really matter as much in the very early stages. That's an example of something that is an important detail that could matter later on, but in the early stages when mass loss is massive, may not play as big a role. So, of course, I always welcome more data. The more data we have, the better. I think sometimes it's good to look at the limiting factors. What are the most important parameters? And then once you kind of see what those tell us, then you can start including those smaller and smaller details. So that would be my answer. That yeah.
Yeah, what I'm afraid of is that we end up like as you very nicely cited in Mordassini paper, said, now we understand it all, and we are about there, but maybe then when we start looking at the different plane, then we again find surprises.
I think the biggest source of uncertainty right now, if we look when is atmospheric evaporation most prominent, it's in the early stages of a planet's life. Mm-hmm. And that's when it's most uncertain. We don't really know the initial surface temperatures of Earth, for example. And we have a lot of data for Earth relative to these exoplanets. So if a planet has a initial temperature of 7,000 versus 15,000 Kelvin, this will play a big role. So I think, I completely agree with you. This is why I'm cautious, because I don't want to be lost in the details. I think beginning with the general ideas is always a good place to start, and then we slowly go towards more and more detailed models. Thank you for your question.
Okay, it's almost time, but we can take one quick question if you have. Okay? If not, let's thank our speaker again.
Thank you.